and welcome to the Liquid Crystals Wizard Show. Well, today we're going to talk about light and lots of different properties of light. And I'm going to start out here with kind of a very special light. So here's a light. You know, I could use it to read a book with, right? So I could put my book here and then I could read my book with this light. But this is kind of a special light, okay? This is a light that we can make pictures with, okay? So it's a display, and I'm sure you've all seen something like this before. So today we're going to talk about how this display makes pictures. And that story has to do with a lot of the different properties of light. Okay, so to begin with, we're going to look at some different lights. Here's a flashlight. I can turn it on and off. And here's a really nice green laser pointer. Look at that. Makes this nice green spot that we can go around with. So let's think about properties of light. So what are some of the things that light has? Or light does? Anybody? Brightness, okay. Light can be dark or it can be bright. Here? What? Shows us the direction we're going. So that's a good one. So light can show direction. So light has direction. So light can be in that direction or it can be in that direction. So light has brightness and direction. What else does it have? Okay, coherency, incoherency. Color? Right, that's an important property of light. Color. Okay, so light has color and it has brightness and it has direction, but it also has another property that's very important, and especially for making pictures like this, and that's polarization. So we're going to begin by doing an experiment that shows what polarization is. And for this, we're going to need 3 volunteers. Okay, there's 1 and 2, and then somebody from the back up there. Right there. Yeah. Okay. So we got our 3 volunteers. Good. Okay, you guys are going to have to just move over a little bit because we're going to use this space right in here.
We have a new innovation.
Okay. Okay. Okay, you guys come over here. That's it. You got to hang on to the end of that thing real tight. And you got to stretch it. You got to move back. Go on. Back further. It's got to be stretched. Okay, so this is our wave machine. So this makes waves. And light is a wave. So this is kind of a long wave, or we can make a short wave by going faster, like that. But the important thing about this wave machine is that it shows polarization. So this is a wave with vertical polarization, okay? Or we can make a wave with horizontal polarization. Or we can combine the two and make a wave with circular polarization. That's circular polarization, like jumping rope. Okay, now for polarization, there's a thing called polarizers. Polarizers that control the polarization. So now we're going to put our polarizers on the wave machine. Okay, so here's a polarizer for this wave machine. You see, it's just a bunch of little sticks put together. So we're going to put this polarizer on the wave machine. Get right in there. Okay, and let's make it go up and down. And hold it on this side, over here like this. Just top one hand here, and one hand there. Good. So now we can see if we can make the wave machine go. So we'll try to make horizontal polarization. Okay, here we go. See, it doesn't work. Can't get horizontal polarization. I can get vertical polarization pretty well still with this polarizer, but I can't get horizontal polarization. Okay, so now let's put another polarizer on. So we have another polarizer. There it is. So we're going to put that on the wave machine. Okay. Let's get our wave machine in there. Okay, so now we've got a vertical polarizer and a horizontal polarizer. So if I try to make vertical polarization, can't do that very well. And if I try to make horizontal polarization, can't do that very well. So with the polarizers crossed, we can't get any waves. Now we could turn the one polarizer, so let's turn that one. That's it. So we'll turn that. Now with the polarizers parallel, now the waves can get through again. So this gives you an idea about polarization and polarizers. Okay, so now we're going to look at some real polarizers.
Thank you.
Thanks, guys.
Thank you. Thanks for the helpers. Okay. So, so now we understand how we can polarize waves. And so let's see how we can polarize light waves. Okay, so here I've got a light, and it's not polarized. So this light is coming out vertical, horizontal, and all the other polarizations. Now, okay, you just saw how this wooden polarizer with sticks can polarize the model wave in the plastic sheet, in the plastic tube. Now this is a real polarizer that polarizes the waves in light. Okay, now it's actually very similar to this one, except the sticks in this polarizer are tiny. They're the size of molecules, but they can block one of the polarizations of light, just like the sticks in this polarizer can. And here, the polarization of light that comes through that is not blocked is marked by this tape. So this polarizer would let vertical light through, the vertical waves, and if I rotate like that, it would let the horizontal waves through. Okay? So now what happens if I have this unpolarized light coming out onto the screen. Now what happens if I put this polarizer in front of the light? Well, nothing very dramatic happens, but of course half the light is being blocked, and so you can see that it gets darker. Okay? But still, half the light is coming out. So now I have vertically polarized light, because here I have my vertical polarizer, and I have it oriented so it's blocking the horizontally polarized light. Only the vertical waves are coming out. Now, of course, here I have another polarizer, okay? And this polarizer, I can have it oriented the same as this polarizer. And of course, if I have two polarizers that are letting through vertical light, then again, not very much happens. The light just comes right through, vertically polarized. They're both the same, just like in the model. But if I take this polarizer and now I rotate it, okay, what's going to happen when I rotate it? Well, if you saw what happened in the model wave, you're going to see what happens. Okay, so now here, the two polarizers are parallel, but if I rotate one of the polarizers, you can see that it blocks all the light, because now the bottom polarizer, which scientists call, this is a very technical name, this bottom polarizer is called the polarizer. Okay? So there's the polarizer. And the second polarizer, we always call that the analyzer. Okay? This is the analyzer, this is the polarizer. If I put the analyzer in perpendicular to the polarizer, I'm now blocking both the horizontal and the vertical light, and so not very much light gets through. Okay? What we really would like to be able to do is change the polarization of light so that it can get out through the analyzer. Okay? So I have my vertical polarizer, then I have my analyzer, which is horizontal. Okay? Now, if I could put some kind of material in between that would change the polarization of light that comes through the polarizer, then something would come through the analyzer. And it turns out that we've known for a very long time that there are certain materials that can change the polarization of light. This is a piece of mica. Mica is a kind of rock that can be cut into very thin sheets, and it's clear. And this is true of many kinds of rocks and minerals. These are solid materials that can change the polarization of light. So if I slip this piece of mica in between the two polarizers, you can see that the mica can change the polarization of light coming from the polarizer. Then the light then gets through the analyzer, and so I have all these nice colors and light coming out. Okay? So certain solid materials, almost all crystals, can change the polarization of light. Most minerals are kinds of crystals, and there are many other things that can change the polarization of light. In particular, plastic can change the polarization of light if it's stretched. Now, when the people that manufacture Scotch tape make the tape, it gets stretched. And so you can do this at home. You all have an optics kit, and you've got a polarizer and an analyzer, so you can do these kind of experiments at home. If you get old-fashioned plastic tape, strapping tape, or packaging tape, not the invisible tape, then if you make multiple layers of this kind of tape, you can get some really nice colors coming through. So this is just pieces of tape, okay? And depending on the thickness of the tape, the polarization that comes, the way it changes the polarization is different, and you get all these different colors coming through. Cellophane. Cellophane is great at changing the polarization of light. This is just a piece of cellophane that you can see that it can let light through or not. This is a plastic fork. Okay? Now you can see that the fork changes the polarization of light a little bit. But it turns out that one of the interesting things about this is that if you squeeze on a piece of plastic, it changes the way the plastic interacts with the light. And so you can see that as I squeeze on the fork, it changes what you see coming out through the analyzer. Okay? And then finally, just simple pieces of transparency medium. If your mom and dad or you have a printer and you have some transparency medium, it's good at changing the polarization of light, but you can see that the orientation of the material sort of changes dramatically the way it interacts with the light. And we can use this property. This property of solid materials that change the polarization of light is called birefringence. It's kind of a big word, but it's called birefringence. And birefringent materials that change the polarization of light, we can use them to make information displays. Oh, now, okay, so over here we have a light box that has a polarizer, and then it has some birefringent materials that are spelling out a secret message. Okay, and you really can't see the message, but if you pull out your analyzer that's in your optics kit, you can use your glasses, or you can use one of those pieces of polarizer, and you look at this. That's the analyzer in your hand. You can look at the light box and see the secret messages that are written there. So you can see that, yeah? I can't hear you. Uh-oh. You better tell another wizard. I had nothing to do with that. So, we have a misspelling.
Well, wizards aren't very good at spelling.
Okay, so birefringent solid materials can change the polarization of light, and we can use this to make information displays.
Okay, so now let's see how we can make a display like this. How can we make pictures using materials that change the polarization of light? So here's a way. So we'll put our... Is the screen supposed to be on? Okay, so here we have our polarizer and our analyzer again, so we can turn the analyzer so it's dark or bright. So we'll put that back in. Okay, and so here I have a little filter. So it's a filter with some colored strips of plastic on. And we'll just take that off for a second. So here's our filter. And so we've got these red, blue, and green stripes. Okay, so we can think of this as a display. It's not a very interesting display. But here's an interesting thing. If the stripes were very tiny, this display wouldn't look like red, blue, and green stripes, but it would just look white. And we'll see that in a minute. Okay, so we have a display, and we can think of it as just being all on. And now, if I put my analyzer in, now we have a display, but it's all off. Okay, so now we're going to turn the display on piece by piece, switching on what we'll call pixels. So there, we just turned on a green pixel. So I have a little piece of this plastic that changes the polarization of light, and if I put it down, then I turn on a little green spot. And I can make several green spots, like that. So now I have a green one. Well, I can make a blue one by moving these over there. Now I have a blue one. Or I can make a red one by moving them over there. So I can make all sorts of patterns and change the colors by putting in these little squares of plastic that change the polarization of light. Okay, so this is the way you can make a display with things that change the polarization of light. Now, one interesting question is, how do you make different colors? So here we see red, blue, and green. Now we're going to look at how a display like this can make any color or different colors.
Okay, thank you, Noel. So Noel just showed you how we can make a display that just shows three colors, red, green, and blue. But of course, as you all know, there's a lot more colors than that, and we want to be able to show all the colors. And what I'm going to try to illustrate now is that, in fact, we can use just red, green, and blue to make any color. This is actually a very important thing. So here I have a red circle, and then here's a green one, and here's a blue one. Okay? Now, what do you think is going to happen if I overlap the red circle with the green? Does anybody know what we get when we get red plus green? Yellow. Yellow. I heard someone say yellow. Okay, now I'm going to try this. So we overlap the red and the green. Well, we get sort of yellow. Okay? It's about the best we can do. All right. Now, here's a blue circle over here. Now, what happens when we overlap the blue with the green? Well, blue overlapped with green gives a really nice color. It gives a color called cyan. That's a great color. Okay? And then if I overlap the blue with the red, we get my favorite color, which was magenta. Blue plus red gives magenta. And then if I overlap all three colors, anybody know what's going to happen if we add red, green, and blue? White. Yay. We're going to get white. Okay, so there it is. So you can see that where the blue and green overlap, we get cyan. Where the blue and red overlap, we get magenta. Where the green and red overlap, we get yellow. And where all three overlap, we get white. Okay? Now, I'm actually overlapping the colors to add them in this demonstration, but it turns out that in a computer display, if you just have those colors very, very close together, your eye can overlap them for you. And by changing the brightness of these three colors and overlapping them in the right way, we can get any color. Okay? So now we're going to try to show you how that happens on a computer display.
Okay, so how does the computer display actually make these colors? That's what we're going to find out now. And to do that, we're going to use this funny TV camera. Okay? So we have a TV camera, which right now you can see is looking at the ceiling. So it's at the end here, but we can turn it down and there you are. So waves to the camera. Very nice. Keep it in focus here. There you Okay, so what we're going to do here is take this funny TV camera, and we're going to have it look at the display, up close and personal. So here we go. So we got to gooseneck this thing around and get it aimed in the right direction. And okay, so here we are. Let's get it straightened out and in focus. Okay, so now here we have our red, blue, and green pixels and our circles, and now we're going to move in here and get closer and closer. You can see this is getting more and more dangerous because this cursor is getting gigantic. Okay, so here we go. Right up, and just about touching. Okay, now I'm touching the screen, and this is as close as I can get. Okay, so let's see if we can get this ooh, there's our giant cursor. Might have just lost it. There it is. I think we got it back. Okay. Okay, so over here, this was the red. That was the red circle. And you can see here we have these pixels, and only the red ones are lit up. So that makes red. Over here, this was the yellow. So this has both red and green lit up over here. In the middle, we have white. So that was the red and the green and the blue all lit up. And then down here, right over in this little corner, that was, what color was this? Magenta. So that's blue and red lit up. And then if we go over here, we just have, down here, we just have blue. And then up here is cyan, where we have blue and green. So these colors come just by turning on pixels. Okay, but to make a display interesting, we have to be able to change things. So when I move the cursor, the pixels turn on and off. So to make a display, we have to be able to turn the pixels on and off. And that's hard to do with little pieces of plastic. We'd have to have like little insects that would move them around. So to make a display, we have to have some good way of having material that changes the polarization of light, but that can be changed. Now, materials that are easy to change are liquids. You know, liquids change shape very easily. We can make them flow. So can we have a liquid that would change the polarization of light? So to see that, we're going to do an experiment. Okay, and so for this experiment, we're going to need, I think, 6 volunteers. Okay, so so here, I think everybody's over there. Everybody's over there. Yeah, over there.
I'm sorry, you guys. I wish we could pick everybody.
Okay, so here are the liquids that we're going to look at.
Those are the guys that picked the volunteers. But
so
thanks a lot.
Water, milk, corn syrup. So things that you find around the house. And then we're going to try a liquid called liquid crystal. Okay, so here are our liquids, and everybody's going to get a liquid. Oop, the wizard just dropped one.
So you will have
3,
okay.
4. Okay, so we need 6.
You will have
I think we got one extra kid, so we'll have to sort of, you guys can do it together. Okay, why don't we start out? So what do you have? Milk? Okay, come on over here. And what we want to do is take the top off. And we can put 2 drops. You can each put a drop. So we want a drop of milk right there, next to where it says milk. Actually over here.
So you can make a drop.
On the glass. Yeah, you can make a drop there. Okay, right there. That's it. Okay, good. All right, next, what do we got? Okay, so that your guys are all done. Thank you. Tap that. Corn syrup, so you want to put a drop right there. Okay, so we'll put these things down, and then we'll see if they change the polarization of the light. That stuff you got to kind of squeeze, I think. You know, it gets sticky. Squeeze, squeeze. There you go. Big squeeze. Hard squeeze. Great. Okay, perfect. All right. All right. Good. What do we got in there? Water. Okay, so you're up on the top there. Great. Okay. You got dishwashing liquid, huh? Good. Okay, you're over there. Great. Okay.
So you share with her. So they can do 2 drops.
Yeah, okay, so you're here. Okay, you can help me with the liquid crystal, okay?
Wow.
Okay, so
Very good. Thank you.
so we got the liquid crystal in this little syringe just to keep it safe. So we're gonna put this on here, and then we're gonna push that in. Just okay. You gotta push this in just a little bit. A little more maybe. Okay, great. Okay, so that's all. Why don't you guys can have your seats back? Okay, so now we're going to see if any of these things can change the polarization of light. So here's my analyzer. So I got it in so it makes things dark. And we'll slide it across here and see what we get. So that's, put it back in up here. Okay, so what do we have here? Well, everything looks pretty dark, except maybe on the bottom here we have maybe a little bright spot from the liquid crystal, but everything else looks pretty dark. Maybe things would be better if we put a glass slide on top of our liquids. Okay, so here's a glass microscope slide, okay? And so I'm going to drop these, cover up our liquids one at a time with glass slides. So there's the first one. We'll just drop that on. Okay. That's the water. And then we'll do the milk. The slide on there and just drop it down. Okay. Here's our corn syrup. Okay, that's getting a little softer now that it warmed up. Okay, now the dish soap, let's see what that's going to do here. Okay, that spreads out pretty nicely. Okay, cooking oil. Okay. And now our liquid crystal on the bottom here. Let me move this up so we can see what's happening. Okay, so now we got all the liquids between slides. So let's see what's going to happen now. Okay, so here's our analyzer again. I'm going to slide this in here. Wow. Okay, so now we can see that everything's dark except the dish soap and the liquid crystal. So both dish soap and liquid crystal change the polarization of light. And that's because both soap and liquid crystals are liquid crystals. So you can see that this is a liquid, so I can make it flow around. And how it changes the polarization of light really depends on how I push on it. So this is a liquid. The liquid crystal is a liquid that changes the polarization of light. And that's why it's used in these kinds of displays. Okay, so now we're going to look at what kind of molecules go in to make a material, a liquid, that changes the polarization of light.
I think so. You can bring the lights up a little bit. Thanks, Noel. Okay, so now we get to see what a liquid crystal molecule looks like and why they might be able to change the polarization of light. Okay. Now I actually have a plastic model of a liquid crystal molecule right here. Now, as you might know, molecules are made out of atoms, and they're very, very tiny. And this is a plastic model of a molecule, but this model is a lot bigger than a real molecule. And to give you some idea of how tiny molecules really are, we've borrowed from a fantastic website from Florida State University. Let me get my molecule out of the way here. Okay, now what you see here is the tops of some trees and some buildings looking down from a very far distance, actually. So we see these trees. Now, what I'm going to do is I'm going to start magnifying this image until we magnify it so much that you can actually see the atoms in plant cells in the leaves of one of these trees. Now, that takes a huge amount of magnification, and you all know how to count, of course. Let's get to the tops of the trees. This is sort of the actual size of the leaves in the tops of one of those oak trees. Now, you all know how to count 1, 2, 3, 4. You probably also know how to count by tens, 10, 20, 30, 40, 50. But in science, we deal with things all the time that are really huge and really, really tiny. And the differences in size are so huge that we often count in what we call powers of 10. And so in powers of 10, you multiply by 10 every time instead of adding 10. And so I'm going to start magnifying this image in powers of 10. And Noel is going to call out the magnification. So
1, 2.
Okay, so we're starting to see the leaf close up.
3.
Okay, there's a really big leaf. We're magnifying 10 times every time.
4.
Okay, now these are clusters of leaf cells.
10,000 times.
10,000 times. We're seeing leaf cells. We're going to zoom in on one
100,000
cell.
times.
Well, there's a few cells. Now we're going to zoom in on the nucleus of one of those cells.
Now we're at 1,000,000 times.
1,000,000 times. And then we're going to look inside the nucleus. This is the genetic material called chromatin. It's made out of DNA.
10 million times.
10 million. Now there's the DNA strands.
100 million times. And 1,000,000,000 times.
Takes 1 billion times. 1 billion times magnification. And now we can actually see the atoms and molecules in the DNA. Okay. Now, these aren't real pictures of the atoms and molecules of the DNA, of course, because molecules are too small to see directly. These are computer-generated pictures of the molecules. And I have a computer-generated picture that's sort of similar to that of a liquid crystal molecule right here. Okay, so this is a really nice molecule. One thing that you can see about the liquid crystal molecule right away is it looks kind of like a stick. And that's not a coincidence. These long, skinny things can change the polarization of light. Okay? This molecule is made of atoms, as are all molecules. You can see the atoms in this computer-generated picture all have different colors. The carbon atoms are dark gray. hydrogen atoms, they're the small ones, they're light gray. Then we have these, nitrogen is blue, oxygen is red, and there's fluorine atoms in this particular liquid crystal, and they're green. And that's a nice, pretty liquid crystal molecule. Now, as I said, you can't see molecules directly. But recently, a new kind of microscope has been invented that actually allows us to get images all the way down to this 1 billion-fold magnification. So we can actually see images of molecules. They're not like seeing them directly, but they're actually images of the molecules. It's called scanning tunneling microscopy. And this is this is one of the best images of molecules that's ever been taken. It was done right here in this building several years ago. These are pictures of liquid crystal molecules magnified 1 billion times. Now, it's kind of hard to see in that image exactly where the molecules are, so I can sort of help you with this. Okay, so there's a molecule. Okay, there's one of my molecules. Okay, now I can grab this molecule, and I can move it around, and I'm going to show you where we think the molecules are in this image. Each one of these bright things corresponds to this piece of a molecule, and the molecule is sitting just right about there. Okay? And in this image, in this sample, the molecules are all lined up in really nice rows and columns like this. Okay? And this object would definitely be able to change the polarization of light because all the sticks are oriented in the same direction. Okay? The problem is that this isn't really a liquid. This is a crystal. As you know, if someone's trying to take your picture and you're moving around really fast, the picture is going to come out blurry. And the same thing would happen with the molecules. And so we have to stick them down, make them stand still. What we do is we make them crystallize. Okay? And so this is actually a crystal of the liquid crystal molecules. And you can see in a crystal, all the molecules are in nice rows and in nice columns. And all crystals are like that, okay? But what about, how do we get this to happen in a liquid? We want all the rods to line up in the same direction in a liquid. How can that happen?
Well, it seems kind of impossible to have a liquid where everything would be lined up. It sounds counterintuitive, and you probably don't believe it. So we're going to have to do an experiment to see if it's possible to have a liquid where things line up. And to do this, we're going to need some volunteers, except that for this experiment, we need the parents, okay? So we need the adults. We have to have 50 adults stand up and come on down to the front. Everybody grabs a tube. So we need 50 adults inside the big circle here, standing up, holding their tubes.
You thought you could just sit.
Good job, everybody. We're going to have to kind of pack in tightly. Close. Right, freeze in. Tubes. Okay, this is great. We have some more tubes over here, I think. Tube wranglers. Tube wranglers are over there. I think
you have to get a tube.
you have to get a tube. Okay, pack-ins. Try to get inside the circle on the floor.
Okay, we got plenty.
Okay. Any more tubes here? Okay. Let's get the tubes back. Okay. All right, everybody. Okay, so everybody have a tube? We need a couple more. There you go. Okay, so everybody's got their tube. So now you see that we're trying to make a liquid, but they just don't get it, right? I mean, they're like
Crystallized.
they're all standing in rows. They're all facing in the same direction. You know, that sounds like a crystal to me. So, you know, the thing about being a liquid is that you have to be disordered. Okay, so we're going to have to generate some disorder. And the way that we're going to do that is by dancing. Okay? And so you'll dance clockwise if you were born on an even, an even numbered day, and counterclockwise if you were born on an odd numbered day, and go around, and we need some music. Oh, great. Got to keep going around. Okay, now freeze. Okay. All right, so now everybody's going to take their tube and just bring it up over their head vertically.
Great.
So that it's going from your, front toward back. Just to get those tubes parallel to the floor. Okay. Okay, that's great. We have tubes parallel to the floor. Yeah, that's wonderful. Now I think we need a little dancing to get some more disorder. Okay. Okay, good, good. All right, so now I'm going to impose a no crossing rule. Tubes are not allowed to cross. So let's manipulate those tubes so that we have no crossing. No crossing allowed. Your tube can't cross any other tube. No crossing allowed. No crossing. No tube above or below yours. No crossing allowed. Okay, that looks pretty good, I think. Great, thank you very much. No more dancing. So the tube wranglers will collect the tubes, and then we'll see what happened here. Okay, so we've been since we collected the molecules in the front of the room, we've been videotaping what's been going on using this camera in the ceiling here. And so here are the parents assembling to be molecules, ordering up in their crystal. So there they are, getting very well ordered. Faster and faster. Dancing. Okay, so here's our tubes, and you see that in the beginning the tubes are disordered. Lots of different orientations. Lots of different orientations. But once we impose the no crossing rule, so if the tubes can't overlap, then now they try to get ordered.
Here's our liquid.
Well, you see that some of the tubes have problems here, but so now we're getting closer and closer to a fluid that's ordered, and that comes just from the shape of the tubes. So finally, I think there we go, the one last sort of stragglers here. And, well, there we go. That's pretty good. Let's give the parents a hand.
Okay, good.
Okay. Now we see we can have a fluid where we have order and we can change the polarization of light. Okay, so the next thing we need is to be able to change how the molecules are oriented. So we have a fluid. Fluids are easy to change, but then how will we actually change the fluid? So we're going to do that with fields, okay? And here's an example of that. So here's a liquid crystal between glass plates, just like we made before. And here's a magnet, a little permanent magnet. So let's see what this liquid crystal cell looks like. So you can see that it changes the polarization of light, and it's a liquid, so I can push on it, and it's pretty fluid. So let's see what happens when we put on the magnet. So we'll put the magnet right over there and let it sit for a minute. Okay, and now we'll take it off, move it over. And you see that the magnet really changed the, the orientation of the liquid crystal. So it changes the pattern of light coming through the glass, coming through the liquid crystal, coming through the glass plate. So magnetic fields can change the orientation of molecules in a liquid crystal. But to do this, it's pretty slow. You can see that I have to leave the magnet in a given place for a minute to get it to change. So magnetic fields aren't that great for making a display because, because they're kind of slow. So what's actually used in the liquid crystal display are electric fields, and we can show you how that works using a model liquid crystal. Okay? So here I have a liquid crystal cell with some molecules. Here are my molecules, except that they're not really molecules. They're actually just grains of rice. But you see they have the shape, the same shape as our liquid crystal molecules. So they're in salad oil. So we have some grains of rice in salad oil. And then there are these two black things here, which are just pieces of metal. And they'll let me put an electric field on these grains of rice. Now, we need something to make an electric field, and we've got kind of something pretty handy here. So we have this little Van de Graaff, and you'll see that, wow, that makes some pretty good electric fields. You can get some big sparks there. So that looks like it should be good for making an electric field. Okay, so we'll do an experiment to see if the electric field can change the orientation of our sort of liquid crystal molecules. So if I drop, so I haven't connected it up yet. So now I'll just, if I drop some grains of rice in here, I put some extra molecules in. You see they're kind of disordered. They don't care which way they go down. Okay, so let's see what happens if we put on an electric field. So if I can get this thing off without getting electrocuted. Okay. So now I'm going to hook up my electric field generator. So we have one wire here that goes from the bottom of this thing to one of these pieces of metal. And then we got another wire here that goes from the top of our Van de Graaff to this other piece of metal. So now, when I turn this on, I'm going to get an electric field on our liquid crystal grains of rice. Okay, so here we go. Wow. Okay, so now we'll add some extra ones, and you see that when I throw them in, they just line up right away. So the grains of rice really want to be along the electric field. So, and that's exactly what happens in a liquid crystal display. So you put an electric field on the liquid crystal, and the molecules line up along the field. And even if you want to mess them up, You know, they just insist on being parallel to the field. So we can throw those guys in there. Okay, so that's how a display works. You put a field on, the liquid crystal molecules line up, and that changes the way light's polarized. So we'll just finish up by so if you get out your optics kits, then you can see that just kind of we have a big liquid crystal cell here, which is switching on and off. Okay, so here we're just switching. We just have a little voltage source, and we're with a battery. We're switching the voltage on and off, changing the orientation of the liquid crystal molecules, and you know, making this kind of little display. So that's how the display works. Now, when we looked at the liquids that change the polarization of light, we saw that liquid crystals did and that the soap did. So soap is a liquid crystal, and Dave is going to tell us a little bit about that.
Okay, so soap can change the polarization of light when it's mixed with water. This isn't surprising because here on the left you can see what a soap molecule looks like. It's also sort of like a stick. The soap is fantastic stuff. It's been around for a very long time, but it has a very interesting way that it works. So part of the soap molecule is made out of carbon and hydrogen. This part over here, remember the light gray is hydrogen, the dark gray is carbon. This part is made out of carbon and hydrogen. We call that hydrocarbon. Hydrocarbon is like oil or grease. And then up here, this top part of the soap molecule, sometimes we call this the tail, and this we call the head. The head of the soap molecule is green and red things. Red is oxygen, green is actually a sodium cation. And this part of the soap molecule is very different from this part. Okay, this part really likes water, and this part down here, it hates water and it likes hydrocarbon and grease. Okay, and over here I've got a soap molecule that I let some waters jump at it, and all the waters went up on the head, and you can see the waters are really trying to stay away from the tails. Okay, now if you take soap and mix it with water, what happens is the heads of the soap that like the water, they go out, they make these little balls. The soap molecules spontaneously create little balls in the water with the outside of the balls covered with those red and green things, the heads, and the inside of the balls is all the hydrocarbon. Okay? So that's what happens when you mix soap with water. Now, you know that if you have greasy dirt on your hands and you try to wash your hands in just plain water, the grease doesn't come off. Okay? But if you have soapy water, the grease just loves to go inside the hydrocarbon part of those little soap balls. And so the grease dissolves inside, and yet that ball, which is very small, it stays in the water because the outside likes water, and then you rinse your hands and it goes right down the sink. And that's how soap works to wash your hands if they get greasy. Okay? But soap does some other amazing things, but you're very familiar with these things. For example, you can get a certain situation where when you have water plus soap, the soap molecules will actually make a very thin film with water inside where the hydrocarbon parts are aiming towards the air. The hydrocarbon actually likes to be near the air, and so you can get these very nice, beautiful, thin soap films. And sometimes those films will wrap around and make a ball, and of course you all know what that is. That's a soap bubble. The walls of the soap bubble are liquid crystal. You can see that they have some properties of a solid, but they're flexible. They're liquid crystal. And so now we're going to try to demonstrate for you a giant 30-foot high soap film. That's basically the end of our show, and we thank you all very much for coming. You're welcome to come down. We have a lot of interesting demonstrations and things. You can come down and play with the soap film machine. You can even get inside a soap bubble. And thank you very much for coming.